Welcome to this video on measuring solar irradiance. By the end of this segment, you should be able to describe how irradiance is measured, as well as visualize and model irradiance and solar energy intensity. Let's begin with thinking about where sunlight is on the Earth's surface. Well, we know that sunlight is subject to absorption, scattering, and reflection. And we know that it's also subject to the air mass. Once we know all of those things, how do we actually begin to measure the irradiance or intensity on the ground? Well, sunlight has been monitored for many decades in the United States and around the globe at stations where sunlight measurements are continuously taken, usually part of larger weather stations, so they get dual use as part of meteorological data analysis as well. Irradiation measurements are not needed at every location on the Earth's surface because solar irradiation is regionally consistent, meaning that it does not change on average for about 100 to 200 kilometers or 60 to 120 miles or so. The data from monitoring systems are used to predict future sunlight intensities, but they're also required for tracking systems to be able to follow the sun in the sky. These data are used to create maps showing sunlight intensity across the US and the globe. This is one example of a solar irradiation map for flat plate, south-facing latitude tilt systems. What this means is there's no curve to the collector system, they're facing due south, and that the monitoring system is tilted at an angle equal to the latitude at that location. So a station in New York State might be at 42 degrees tilt, but a station in San Diego, California might be at 32 degrees. This color map from NREL for the United States shows the highest sunlight energy in the southwest and where the least sunlight is in the northeast and the northwest. Energy levels are shown as a daily average over the course of a year in units of kilowatt hours per square meter per day. So this connects back to our full sun hours and is essentially a measure of the sun hours per day. We can also improve performance using a tracking system, which moves the collector throughout the day to always receive direct irradiation. Looking at this map, we see dramatic increases in solar irradiance in the southwest. However, what's quite interesting is that the level actually goes down significantly in the northeast and the northwest because tracking favors direct irradiation. There are very few cloudy days in the southwest, so there's more direct irradiance and the collectors can align directly with the sun wherever it is in the sky. Under diffuse cloudy conditions, global sunlight is dominated by the indirect factor and spread more evenly across the sky. Angling the collector away from due south actually limits the amount of available indirect light, and there's a negligible amount of direct sunlight that's available. The maps generated by these monitoring systems help us to visualize average solar energy levels, but we can also make spot measurements in the field. We might want to do this because it helps us to evaluate photovoltaic system function and if there's any issues with the PV system. There are a few meters out there in the market. This is an example of the Daystar brand meter. The meters are calibrated to show solar irradiance in units of watts per square meter. They're small, about the size of a pocket calculator, and they can be mounted in any direction to match the angle of the solar collector and measure the intensity of sunlight. As a reminder, if you can compare the watts of electricity coming out to the watts of the sunlight coming in, we can get an overall efficiency of our system. This is something we discussed how to do in the first course. In the next lesson, though, we'll start to look at how online resources can be used to get this irradiance data and correlate the amount of sunlight intensity to where it is on the Earth's surface.